of the traffic that usually happens in an area. So this module here can be trained under several conditions. You can have, let's say, it can be trained under the average travel time. So this defines the time it took for an individual to travel from point A to point B. Or maybe you can train it based on volume and flow. So this defines the number of cars that have passed point, the number of cars and what type of car it happen to be. Then you have congestion patterns. So this defines the accumulation of people in one area. So if this, like, normally a lot of people in one area, we most likely are going to expect there to be traffic in that certain area. Then you have the trip destination details. So this defines the initial trip starting location and the final destination. Then we have the speed policies. This studies the speed policy given along a given road. So real-time and dynamic data, that is what is happening right now. So this data trains the model to identify the current conditions and to react to unexpected events, which are contingencies. So this data is captured by using several methods, such as the use of a sensor, or maybe the use of traffic cameras to count the number of cars that are coming, to measure the speed, and to record the type of car that is passed through, let's say, a road or a highway. So also accounting for the unexpected events, such as the accidents, that can also be recorded to help the module make more accurate and reliable data. So this can actually be done manually or automatically. So automatically, the data can be recorded using camera feeds from traffic zones. So these are used to analyze the state of traffic, or we can get the data manually, or the data can be recorded by documenting traffic stop management from the traffic stop from the police traffic stop centers, or the user reports, or the police stop records. So contextual and static data. So what is the weather like in the particular area? So this data here helps to train the module on external factors that have the ability to affect traffic. So this can be for example, the number of lanes that is there in that particular road. Maybe social events, what's happening in the area. If there's like a gathering or there's like a function, we expect there to be traffic. Then there's a point of interest. So the areas that attract large groups of people, we normally expect there to be traffic. Then there is road types, presence of traffic lights, and amongst others. So this helps the module to operate under the rise of unexpected events. Temporal and event data. So what day it is and what's going on. So this helps to train the module on the concept of timing. So this helps the model classify between time, day, weather conditions, and visibility. So whenever it's classifying time, it analyzes traffic patterns during rush hours, peak hours, and normal hours. So everybody knows that during rush hour, there's a high chance, there's like an 80-90% chance there's going to be traffic, because everybody's going to the workplace or they're coming back home. So most definitely there's always going to be traffic during rush hour. Also, there's also going to be, we should also expect traffic during peak hours. That's why there's a lot of people going back and forth using like a road or a path. Then the day of the week. So this one, day of the week, this helps to identify the days with the most and the least traffic. So let's say our module, basing on previous data and patterns, fed into it. It's identified that, let's say, Mondays and Tuesdays and Wednesdays, Mondays, Tuesdays, and Fridays, these are the days whereby there's so much traffic. So whenever you come to use the module or the module, and it happens to be one of these days, then it will give you an accurate reading or an accurate assumption or prediction that you're going to encounter traffic. So you need to be ready for that. Then you have weather conditions. So this is analyzing the traffic patterns during certain weather conditions. Then we have the visibility. So the applicability of the data by the AI module. So by making use of the different categories of data the module is able to learn from these complex relationships, this gives it the grounds to be able to produce more accurate and reliable outcomes or outputs. So for example, our case study here, let's say we're traveling from Entebbe to Bunga, let's say via the Entebbe Express Highway at around 5 p.m. So the system can predict that the possibility of traffic based on analyzing historical traffic patterns on that particular road. It therefore can come up with an alternative to try to help us avoid traffic, hence redirecting us to a different road. So the module 5 talks about first order logic, or the FOL. So the FOL helps us to define components and their relationships, hence making it precise and symbolic statements about objects such as roads, vehicles, their properties and their interactions. So the problem in question here for our traffic prediction module, it can be conceptual, can be put into 3 different aspects. So one is the universal discourse, which is the domain objects. So it can put into functional basis set, which is the functions of a domain, can be put into relational basis set. So this does the relations between the objects. So going on about first order logic. So the module is built and defined by the following. So one is we have to first define the domain. So we have to define the constants that's in question and the objects. 2, we have to define the predicates, so the properties and the relationships. 3, we have to define the functions, those are the returning values. 4, we have to define the first order logic rules and regulations. So beginning the domain constants and the objects. So this usually requires us to identify the types of objects, the types of constants that we are working with that is existing in the domain. So for our traffic prediction model here, let's say it contains the following. It can contain, for example, objects like roads or vehicles, and then we have time, then we have events, then weather condition. So then we can have constants as, let's say, R1, R2, R3, representing a specific road. Then we can have V1, V2, and V3 representing specific vehicles. Then T1, T2, and T3 representing accidents, amongst others. So defining defining functions. First order logic rules and axioms. So axioms here are facts and rules capturing important domain knowledge. So this is assumed to be true without proof. Then foundation of deriving other truth. So the theorems here we usually have the well-formed formulas, which are provable from the axioms. Then we have derived through logical inference rules, which are extended through knowledge beyond basic axioms. So then we move forward to module number 6. So module number 6 talks about the inherence in first order logic. So this is a segment that deals with defining the domain and the vocabulary which is used in the domain and the problem segment. So these are defined into groups of constant variables, predicates, and functions that describe the traffic environment. So underneath it all, underneath all of this, we have the axioms, which contain the general rules which will be followed when developing the module and the specific facts. So for the general axioms, what are other rules? We have 1, we have the congestion definition. Then 2, we have the congestion propagation, which is the upstream. We then have the flow. 3, the flow conversation. Then 4, we have the temporal persistence. So inference in first order logic, this uses FOL to build a formal interpretable and logically sound traffic prediction model able to be used for predicting and reasoning. So this can be achieved by using key components on how to perform inference. So the procedures considered during inference, we have to first define the domain and the vocabulary. So this helps us define the objects and concepts in our traffic prediction module to the real world. So this can be constants, predicates, or functions, amongst others. Two, we have the core enzymes and rules of the module. So these are the rules that define and govern the fundamental physics and the logic of the whole traffic prediction system. So this can be achieved by the application of distinct rules set. So the core axioms and rules of the module here, we have 4 different. So we can have, this can be achieved by the application of distinct rules, such as, for example, following distance. 2, we can traffic light behavior. 3, we can consider propagation of congestion. 4, we can consider lane changing. So the axiom rules and the core axioms and rules of the module, we have performing inference for prediction. So this is the process of using the known facts and rules to better manage and develop the module. So how all this comes to work, we have the knowledge base. Those are collection of the facts and rules. We have the unification. We then have the application with all the modules penance. We then have the chaining. So the strengths and limitations of the FRL module. So the strength of the FRL module here, we have, it can be it easily handles uncertainty. So with extensions, it is easy to interpret and it's easy to explain. So it's very easy for someone to understand and be able to make sense of it. We then have it sounds formal and it's formal and sound. Then we have the limitations of the FRL module. So it's static in word assumption, and then it requires complete knowledge. So it's going to take time for the person to get to learn what's being taught and what's being given to them. We then have computational complexity, which can be from errors, which can be complex code, amongst other things. And then we now go to module number 7, or module 7. That's the reasoning and the uncertainty. So the whole module here is based on probability and the utility theory. So the probability theory here, it handles uncertainty about facts, whereas the utility theory, it weighs desirability of outcomes. So what is most desired by the individual. So these two combined together enables a rational decision making under it enables rational decision making and the certainty. So the sources of uncertainty when it comes to choosing or when it comes to decision making can come from, let's say, laziness. That's too much work to determine exact truth, or it can come from theoretical ignorance. So we have no complete theory available to back up our claim. Then 3, we have practical ignorance. Even with the theory that we have, we can't determine exact values and factors. So that also becomes another factor. So the first order logic, or the FRL limitations, it has about 3 limitations that we have noted so far. Yeah, first of all, it assumes complete knowledge. That's the thing. Right off the bat, it just seems that the person who's going to be handling it they already have prior knowledge, which is not the case most of the times. 2, it cannot handle degrees of belief. 3, it fails in complex uncertain domains. So unexpected events such as contingencies, maybe accidents and stuff. So it doesn't account for that. We then have the basic probability concepts, where we have we have the discrete, continuous. These are random values of probability. So the discrete here, we have infinite number of possibilities, and then we have continuous, which are the infinite number of possibility values. So module 8 is the planning. That's the third last module in our segment for the course. So for the planning here, this is the segment that deals with the crucial steps being taken to oversee the final development of the final development of the product. So here we aim to bring together all the resources and all the data and all the information about the model which we want to develop, so that we can find a way forward, and then plan to develop the module, so that we get to the final product, a working product which is able to give us, which we're able to put in inputs, and it produces reliable and accurate outputs. So the classic for